Hello again. This is Michael Creutz. I'm going to give you lecture 4 of my sequence of 4 lectures for the INT's summer school on lattice physics. I guess I might as well just go right into it. There we go. Okay, this is going to be about some issues that arise when you try to put some of the ideas of chiral symmetry I talked to before with some of the ideas of the lattice fermions I talked to before. So this is a screw from chiral symmetry, and this is our lattice, and they're fighting with each other. So I'm going to start by talking about some of the pseudoscalar mesons in this theory. And let's consider just the 3-flavor theory for simplicity. And you go and you look at the Gell-Mann matrices, and you discover that the neutral mesons are different combinations of U bar U's and D bar D's and S bar S's. I naught is a U bar left, U right, U left. And the minus sign is to make it pseudoscalar, and this minus sign is to make it isospin 1. The eta brings in the strange, and you see the Gell-Mann matrix hidden in here, the 2, -1, -1. Whoops. And finally there's the eta prime, which is a more symmetric combination of them all, which is the one that's heavier and gets its mass from the anomaly. Okay, now every one of these particles has a U bar U in it somewhere, which means that the operator U bar U, U left, U right, can create a pi naught, it can create an eta, create an eta prime, any one of them. Similarly for D bar D. So I can look at some interesting processes. I can, for instance, create these 3 guys with a U bar U. And then I can destroy them at some later time with a D bar D. Now if you think about it for a minute, this is a spin flip process. It's changing the spin of the up quark from left to right, and this is changing the down quark from left to right. And even for massless quarks, this will not vanish because these particles are all there and they all contain these things. And this is actually a consequence of something called neutral vertex, where the spins can flip for a bunch of particles. Anyway, this has interesting consequences because you can now take this diagram and turn on a small down quark mass. I'll move my microphone closer. And then you can close this down loop on this side with a mass term, because the mass term's left and the right. So we get a process here where you can turn a left-handed up quark into a right-handed up quark. What changes a left-handed quark into a right-handed quark is a mass. So it is, in essence, a non-zero down quark mass can shift the up quark mass. So there's a message here. QCD is determined by the physical particle masses, the proton, the pion, the kaon, etc. The other parameters, mu, md, and ms, are abstract input parameters, and their values can depend on the details of your cutoff scheme. This is well known for lambda and a little bit less known for the masses. And they can get, these parameters can get mixed together. So some understanding of this can come out of exploring something called the Dashen phenomenon. It was actually invented before QCD. Let's look at lowest order chiral perturbation theory, where the pion mass is proportional, pion mass squared is proportional to the average of the up and the down quark mass. That's a very old result. But this is an interesting little formula, because you see that the mass remains finite if I turn off the up quark mass at fixed MD positive. And I can even make the up quark mass a little bit negative, and I still get a nice positive number if the down quark is positive. Now, I told you in earlier lectures that a negative quark mass means you're at theta equals pi. So in this particular theory, going to theta equals pi when the up quark is lighter than the down quark does not do very much. When you get it all the way down to minus the down quark mass, I proved the other day that there will be a spontaneous CP breaking. So it's interesting to ask what happens between mu being MD and mu being minus MD. Well, isospin breaking starts to occur. So the pi naught is a little bit lighter than the charged one because of this mixing going on. And this is actually higher order in the quark masses. It goes as the difference of the quark masses squared. And so here's the down quark mass. I'm sorry this font is too small. But and as we lower the up quark mass, and that's this axis, the pi naught will get a little bit lighter. And as you hit 0 for the up quark mass, well, the pi is a little lighter than the charged thing, but they're pretty close. But if you keep going, eventually the pion can become massless. So the pion can actually vanish in mass before you get to mu being minus md. Now what happens when a scalar particle or pseudoscalar particle gets negative mass? You get spontaneous symmetry breaking, just like in the good old-fashioned Higgs mechanism. So once the pion mass squared is negative, a pion condensate will form. You get an expectation value for the pi naught. Now pi naught is a CP odd particle, so CP will be spontaneously broken. Now formally this is occurring at theta equals pi because the product of the quark masses is negative. I've got the up quark being negative and the down quark being positive. And this was conjectured at by Dashen way back in 1971, just using chiral algebras and things. He did not know about quarks at the time. They weren't really popular. Now this phenomenon actually occurs, very easily to show it occurs, in sigma type models. But the picture is something like this. Here's the up quark mass parameter, the down quark mass parameter. And as you vary the up quark mass with a non-vanishing down quark, so we're going to hold the down quark mass fixed up here somewhere. We're going to come sliding in. You go through the origin without anything happening, and you go far enough, you hit this funny condensate. So this is pi naught condensate in here. It's at negative up quark masses and positive down quark masses. Okay, so it's interesting to look at the symmetries of this diagram. First of all, I can interchange the up and the down quark. That's just isospin symmetry. So I'm symmetric about a 45-degree axis here. I can flip the signs of both masses. That's a flavored chiral symmetry generated by the tau 3. And that takes this side of the diagram and turns it into that side of the diagram. And so there's again a diagonal, which is symmetry here. But that's all the symmetries this diagram has. In particular, there is no symmetry under flipping just the sign of one of the quark masses. I take an up quark mass and minus up quark mass. I go into this crazy phase. This is a strictly non-perturbative effect. A non-degenerate massless quark, there is no protection from renormalization. Symmetries do apply multiplicative mass renormalization of some things. For instance, the quark mass difference, that is controlled by a symmetry, isospin symmetry. So this thing gets multiplicatively renormalized. The quark mass average is the other symmetry, symmetry under flipping the signs of both of them. So both of these are additively renormalized. But there is no reason for the renormalization factors of these two quantities to be equal. They can be different for the iso vector mass difference and the isoscalar mass. And this means that in your renormalization procedure, the quark mass can acquire an additive shift, and the details of that depend on the details of how you've regularized it. With Wilson fermions, it's pretty clear how this happens. There's an additive renormalization from the outset. The kappa critical, where you make the particle massless, does get shifted. And the amount of this shift depends on the details of the coefficient of the Wilson term. Now, overlap fermions depend on the kernel. They have the Wilson parameter in there, so it's really the same dependence for the overlap fermions. Staggered fermions do not have this problem. The reason is there's an inherent degeneracy between the two chiralities of the four states come in two different chiralities, and that cancels the effect. So you can only work with even numbers of staggered fermions. All right, this is kind of interesting because it says quark masses are a little bit dependent on how you're doing things. But you shouldn't really care. You don't really measure the quark masses directly. You measure them, the masses of the physical particles, and you can tune the up and down quark masses with some particular scheme to get the pions right, including the pion mass difference between charged and neutral. This is tied to the fact that the gauge field topology, which is what's generating these non-perturbative effects, is a little bit fuzzy. You can go back and look at the formulation of the path integral, and you discover that a typical path, even in a particle and a potential, is non-differentiable. As you take the continuum limit, the average derivative of this thing goes to infinity. It's really only the particle masses and the scatterings that you should care about, and those are the physical things, and you just adjust your abstract Baire parameters to get them right. It also has some other interesting consequences. At this edge of this funny phase, you have a second-order phase transition. Second-order phase transitions involve long-distance scales. There's a divergent correlation length here. This divergent correlation is occurring when neither the up quark or the down quark are massless. One of those negative and one's positive, but they're not zero. This means you can have long-distance physics without any small Dirac eigenvalues in your Dirac operator. This is occurring where there are no small eigenvalues. The fact that there's no structure at m equals 0 and md is non-zero means it's possible that there's basically no structure there, even though there could be small Dirac eigenvalues there, but those must somehow all cancel each other. This effect, of course, is automatically included in lattice simulations because we're really non-perturbative and we sum over all possible configurations. This is actually an old point. It's been raised many times over the years. My first paper on this was 2004, so they're much older ones. And it is non-perturbative. And it has some important consequences. One, mass renormalization is not really flavor blind because the flavors do affect each other. You can try to do a mass independent renormalization, and you're allowed to, and I will mention that in a moment. But it's got to be a little tricky if you want. It's going to hide this effect of the up and the down quark on each other. But it does mean that there are inherent ambiguities in defining what you mean by a vanishing up quark. It also means that if you try to match perturbative to non-perturbative effects, can fail because perturbatively you cannot see this effect. In perturbation theory, the effect of the quark and the down quark are completely independent of each other. So this was sort of the main point, but now let me just discuss some specific issues which people might bring up. First of all, we're not talking about the Baire masses here, and the reason is we have to talk about the mass at some scale. And the reason is the Baire mass itself actually vanishes, because by renormalization group, the Baire mass goes as the coupling constant is some power, and these are known numbers. And the continuum limit is taken when both the coupling constant goes to 0 and the mass goes to 0. They have to go to 0 together. Since the Baire coupling is going to 0, the Baire mass is going to 0. So you can only really define the mass at some finite scale. Now, it is possible to force, because it's only the first term in this gamma function for the renormalization group, which is independent of scheme. And so you can force yourself just to look at the first scheme, and in that case, the way the masses flow is in fact independent of each mass. If I don't allow any non-diagonal terms in gamma. So technically you can do this, but it really obscures these effects I'm talking about here. The fact that the down quark can affect the up quark mass. And in particular, these quark mass ratios in one particular mass-independent regularization may be constant ratios, but that ratio can depend on the scheme. For example, I told you at the beginning, if the up quark mass vanishes and the down quark mass doesn't, it will get a mass from this mixing, and therefore this ratio will go from 0 to some other number. Now the lattice itself is not a mass-independent independent scheme. So it really becomes unclear in the lattice approach how to do this matching with perturbative numbers, and you shouldn't do any comparison with perturbative numbers. How big is this effect? Well, it's controlled by this splitting between the eta prime and the pion. It also requires isospin breaking, so that MD and MU have to be unequal. So let's just toss in some numbers and see what happens. So say we work at a scale of 2 GeV, which is sort of common. This shift is going to be proportional to this difference. It's going to be proportional to that, and it's proportional to the scale we work at. So this is a number which winds up being on the order of an MeV. So this is not all that different from what people quote for up and down quark masses. Now, people have pointed out that at mu equals 0, there's no theta dependence. Rotating all the phases into the up quark mass leaves us with 3 parameters in the theory. The real part of the up quark mass, the imaginary part of the up quark mass, and the down quark mass. But as I've been arguing, the real part of the up quark mass is a little bit fuzzy. And that means that mapping these things into the conventional parameters is actually a singular map. The usual parameters are mu, md, and theta. But there's no singularity at mu equals 0 that implies there is no natural origin for these polar coordinates. Now in the real world, we know we need to use polar coordinates. They really only make sense if we have a natural origin. Now for the universe, there is a known natural origin. Salvador Dali pointed that out some time ago. The natural center of the universe is the Gare de Perpignan. So here's the Gare de Perpignan, and there's a little statue of Dali up on top of it. And he made this painting where he is at the center of the universe, because that is the center of the universe. And most people are not going to understand this picture at all, so let's go on. So you can try other things. You can define vanishing quark mass by looking at vanishing topological susceptibility. But the topology also has a scheme dependence. You can try and get it from small real eigenvalues of the Wilson operator. But what is small? They're not quite 0 for the Wilson operator. You can try to do it from the real eigenvalues of the overlap operator, but again, the overlap operator is not unique. It depends on which Wilson operator you started with. Now you can smooth things out. This is all due to fluctuations that these MBAs occur, and there's something called Wilson flow, which is actually very popular these days. But even this is not unique. You can ask, well, which action should we cool? It's conventional to cool with the Wilson action. But how long do you cool? If you cool too much, can your topology fall through the lattice? And for the same reason, well, I guess I already said that, the overlap operator is not unique because it depends on which Wilson operator you use. So it's a little tricky to define mu equals 0. So this is going to be a shorter talk than the other ones, because I think it's probably going to stir up some discussion, because not everybody is happy with these statements. But several non-perturbative phenomena get really intricately entangled. The question of theta, the question of whether a quark mass can vanish, the topology of the gauge fields, all these things get kind of entangled. And perturbation theory can mislead because these mass mixing effects are absent. The fact that there's no structured mu equals 0 and md is not equal to 0 means it's very difficult to define mu equals 0. And since it's not defined, how can it be a possible solution to the strong CP problem? And finally, I think I've trying to argue that there's really a very fascinating phase structure when you go into the negative mass quark region with this possible pion condensation. Okay, that is basically the end of this lecture, and you're going to have lots of discussion when we get going in the actual live sessions. Thank you again for listening to this, and I will be gone now.